Hey everyone, so we're picking back up from where we left off last. So just hopping right in, we're going to be talking about the digital electronic basics, looking at binary numbers, logic gates. So this part of the lecture, we're going to be going through a couple examples, and let's hop right into it. So basically, all robotic controller systems, they rely on digital electronics, meaning they use two discrete voltage levels that each one represents the data. So logic 0 represents low or 0 volts. Logic 1 represents high, often usually something over 5 volts, sometimes 3.3 volts. This is like based off of our Arduinos. So digital systems, they're built from billions of tiny transistors that switch between these two states. So by combining these on and off states, we can represent complex operations like comparisons or decision making, all in binary form. So this binary representation makes digital systems faster, a lot more reliable, and easier to replicate than our analog ones. So our binary number system, computers and robots can only read in a binary number system. So this system only has two digits, just zeros and ones. Each position is represented by a power of 2. So for example, let's say we have the binary number. We have this binary number right here, 1, 0, 1, 1. So let's look at it and try to figure out what it is in decimal form. So in decimal form, when we look at it, how we would figure that out is we look at each place. So each place is to the power of 2. So right here, this would be 2 to the power of 0, because that's the 0 position. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So 2 to the power of 0, that's just going to be 0. 2 to itself is just, 2 to the power of 0 is 1. This is 2. 2 squared, 4. 2 cubed is 8. So what we're looking at here is we're trying to see, what we're multiplying by. So for right here, 8 times 1, that's what we're going to do here. So 8 times 1, and then we do 4 times 0, 2 times 1, and then 1 times 1. So 8 times 1 is 8, plus 4 times 0 is 0, plus 2 times 1 is 2, plus 1 times 1 is 1. So then we just add all of this up. 8 plus 0, that's 8. 8 plus 2, that's 10. 10 plus 1 is 11. So this is how we got to 11. So when we look back here, you can see our decimal number is 11. What does that look like in a binary number? It was our 1, 0, 1, 1. And this is all in a base system of 2, so that's why we're doing everything. Each position is to the power of 2. So again, binary is perfect for electronics because transistors can easily represent these two states on and off, current or no current. Let's look a little bit more into this. So we're going to practice the relationship between binary and decimal systems. To convert binary to decimal, you're going to multiply each bit by its corresponding power of 2 and add the results. So to convert decimal to binary, you're just repeatedly dividing by 2 and tracking the remainders. So let's look at this example here. So our binary number is 101001. You always start off on the right hand side because that's going to be our smallest digit. So you don't read it left to right, it's right to left. So we can see here when we're looking 2 to the power of 0, what is our output? It's 1. we're timesing that by 1 because we do have a number there. So 1 times 1 is 1. And then here we have there's 2 to the power of 1. That's 2. 2 times 0, because that's what we're multiplying by. That's 0. Okay, so then we just kind of keep repeating that over and over again. You're just multiplying it by 0, 1, whatever the power is, until finally then our next step is you're adding all those numbers together. So we do 32 plus 0 plus 8 plus 0 plus 0 plus 1 gets us 41. And decimals are to the 10th, so that's why we have this 10 here. Let's do another one. Let's break it down a little bit more. Let's convert the binary number. So we have here binary to, let's do binary to decimal. So I'm going to take this binary number here. Let's do 1, 1, 0, 1, 1. Let's get another space. So I'm going to break this down. And then keep in mind, so this is going to be what our binary number, this is typically how you would write it. You want to make sure you don't forget that too. And that's just telling us pretty much like, hey, everything's in complements of 2. So we're starting off here. We are doing 1 times 2 to the power of 0. This position is going to be 1 times 2 to the power of 1, 0 times 2 squared, 1 times 2 cubed, and then 1 times 2 to the 4th. And then below that is going to be what our answers are for that. So 1 times 1, because that's 2 to the power of 0, is 1. 1 times 2 is 2. Oh, I don't know what happened there. This is just automatically 0, because 0 times anything is 0. And then 1 times 2 to the power of 3, that's going to get us 8. 1 times 2 to the power of 4, that's just 16. So what we're doing here now, let's fix this. Is we're going to add all that up. So 16 plus 8 plus 0 plus 2 plus 1 equals 27, and then 10, because again decimal is to the 10th place. So that breaks down that one. Moving on. This is, let's convert a decimal number over into a binary number. So like I mentioned earlier, everything's just divided by 2. So I mentioned earlier, everything's just divided by 2. So let's look at our binary number system. So for this example here, we see we're starting off with a decimal number of 45. We're doing 45 divided by 2. That gets us 22. It's not exactly 22. There is a remainder here, but we're not looking at that because that remainder automatically just gets converted pretty much yes or no. Is there a remainder? If there is, then you put a 1 for the binary spot. If there's no remainder, then you end up putting a 0. So then we just take that 22 divided by 2. We get 11. Is there a remainder? No. So 0. Take the 11 divided by 2. You get 5. There would be a remainder. So 1. And you're just repeating this process over and over again until you can no longer divide that number. And then you'll get your binary number. So I want to look at another example. Let's see here. we're going to do is, let's do the, so this is decimal to binary. And let's do 30. So what's step 1? We're going to do 30 divided by 2, which equals 15. Is there a remainder? So let me put this here. No, there's no remainder. So that means our binary number will be 0. Okay, so then 2, it's 15 divided by 2. So that equals 7.5. We do have a remainder here. So yes. So that means we get a 1 for that position. Step 3, we're just going to take the 7 because that remainder got taken over by that binary number. So you'll do 7 divided by 2. And we already know this is going to have a remainder. That is 3.5. So yes, we have a remainder. We get another 1. Step 4 is taking 3 divided by 2. 3 divided by 2 is 1.5. So we have yet another remainder. So another 1. And then our next step, it's 1 divided by 2. That is also going to have a remainder. I'm not sure what happened there. So yes. So we get another 1. So that gives us our binary number. So we're reading this from top to bottom. So the first one we place is our 0, 1, 1, 1, 1. So the decimal number 30 equals this in binary. So let's say our number gets too big to represent in just binary numbers. It can get really confusing to look at a bunch of zeros and ones. You can see here, like, it's hard to keep track of everything. That is quite a bit. So let's look at this number here. So the decimal number 4,813 can actually be represented by the number 12 CD. So we can look here in a binary, our binary chart. The numbers 0 through 9 will still be represented just with typical binary numbers. However, letters A through F, so 10 through 15, we actually represent with these letters. And this is what their binary output is. But again, if you're combining all of this, it starts to get a little bit confusing to look at. So that's why we use this hexadecimal system to just help kind of keep everything a little bit more organized. So I want to look at an example for that. So let's take our hexadecimal number 12 CD, and then let's convert that. So we were looking at, do everything by the power of 2. This time we're doing everything by the base system of 16. So it's by, 16 by the power of, so whatever the place number is. So either 0, 1, 2, 3. So you can see the numbers get pretty big. The first step is to usually convert your CD to what their actual number place is. So if you go back here, let's look at C. So C would be, we have, so A is 10, 11, 12. So C is 12, and then D would be 13. So going back here, we have 12. We'll be multiplying 16 by 12, and then this 16 to the power 0 is 1, so 1 times 13. So same thing as we were doing before, you're just multiplying everything, and then you add all that up to get our decimal number. Let's do one more example. So let's do, this is going to be hex to decimal. Let's do this one. We'll do 1D 2E. That's all to the base of 16. So the first thing I want to do is look at these two numbers, or two letters, and convert them over to numbers. So D equals 13, and then E is going to be 14. So now we can, when we're writing down the numbers, we can write them down as 1, 13, 2, 14. And I always do this where I just kind of separate everything into their own columns. This just keeps like all the math organized. You can do it however which way you want. This is just how I do it. It helps me. So what we're gonna do here is this is our 0 spot. So that means this would be 16 to the power 0, 16 to the power 1, 16 to the 2 squared, 16 cubed. So once we have that, you would do 16 to 0, it's just 1, so 14 times 1 equals 14. And you're just kind of repeating that same math over and over again. So I'm not going to show every step here, but 2 times 16 to the power 1, that is going to be 32. 16 to the power 2 times 13, 3,288. And then 16 to the power 3 times 1 is just going to be 4,096. So then all that we're doing here now in our last step is we're adding all these. So 4,906 plus 3,028 plus 32 plus 14 gets us 7,470. That's all to the base of 10. So we took this hexadecimal number and then converted it over to decimal over here. Let's actually do one more example before we get into logic gates. Let's do hexabinary. So let's just do a simple one. 1D. So we know what 1 is represented by in binary. 1 is just it's the first digit in a binary system. So everything is also done in like groups of 4. So it would be 0, 0, 0, 1. Now D, we can go look back at our chart. We can look at it back on our chart and just see D equals 1, 1, 0, 1. But if you want to actually figure it out, we'll go through that step and figure it out. So looking at that, we know the answer is supposed to be this. But to figure that out, we can just do what we've been doing, just kind of write down the number. I know this position is going to be 2 to 0, 2 to 1, 2 to 2, 2 to 3. So that would be 1, 2, 4, 8. I'm multiplying 1 to 1, so that is 1. 0 to 2 is just 0. 4 to 1 is 4. 8 to 1 is 8. So when you add all of that up, this equals 13, which D represents 13. So 1D in binary is 0, 0, 0, 1, 1, 1, 0, 1 to the base of 2. So I'm going to end this video here. Actually, let's do one more. I think I missed one more. I don't think I've shown you binary to hex. So let me do that, and then we'll end this video. So binary over to hex. So we have here, let's use 0, 0, 1, 1. Yeah, so 1, 1, 1, 1. So let's break it down into doing this group first. So 0, 0, 1, 1. So 2, 0, 2, 1, 2, 2, 2, 3. That is just 1, 2, 4, 8. But we're only, you can see these are already going to be, these are going to be zeros. So I'm not really going to do the math for that. All I'm going to do is just care for this. So 1 times 1 is 1. 2 times 1 is 2. Add that together, you get 3. Now let's look at this group over here. So 1, 1, 1, 1. So same deal, 2, 0, 2, 1, 2, 2, 2, 3. That it would be 1, 2, 4, 8. So everything gets, all of this is 1s, nothing's multiplied by 0. So all we have to do is just do 8 plus 4 plus 2 plus 1. Let me fix those. So that all equals up to 15. So remember, A through F is equal to 10 through 15. F is our last one, so the representation of this binary number would be 3F. Okay, now I'm going to go ahead and end the video here, and then we'll move on into logic gates in the next lecture.